Okay, we are going to go through 4 examples of graphing rational functions, and everywhere you look, you're probably going to find a different set of steps that they'll ask you to go through in order to graph a rational function. But these are some of the key steps. This is what we're going to use in these examples in order to graph the function, and this will give you a basic sketch of the graph so that if you had to match it to something or if it asked you for a basic sketch, this is all of the important points on the graph. So we are going to begin by finding the domain. Please remember that finding the domain of a rational function, it would be anything except the numbers that make the denominator equal 0. So what we do is we take the denominator and set it equal to 0 and solve it, and that's the number excluded from our domain. So our domain is all real numbers except for 3. Okay. So there's our domain. We can use any number when we come later to our graph except for the number 3. Find any holes, vertical asymptotes or slant asymptotes. There are no holes in this graph, and I can tell that because in order to find holes, you cancel any common factors from numerator and denominator, and there aren't any. There are also no slant asymptotes. I can tell that because slant asymptotes occur when the degree of the numerator is just 1 more than the degree of the denominator, and in this case it is not. So there won't be any slant asymptotes. So let's start with our vertical asymptote. Vertical asymptotes are where the denominator equals 0. So again, just like we did with our domain, we'd set the denominator equal to 0 and solve, and we see that there is a vertical asymptote at x equals 3. Horizontal asymptotes, you look at the degree of the numerator and the degree of the denominator. In this case, our numerator has degree 0 because there's no x there, and denominator has degree 1. Anytime that the degree of the numerator is less than the degree of the denominator, like we have here, your horizontal asymptote will be at the line y equals 0. Next, we're going to find any x and y intercepts. To find x-intercepts, you set the function equal to 0, or you let y equal 0, basically is what we're doing there. And when you're doing this, what will happen every time with a rational function is you'll multiply by the denominator to remove it, and you'll get the numerator equal to 0. Okay, so one shortcut there when you're finding x-intercepts is just set the numerator equal to 0. Now notice we get 0 equals 4, which cannot be solved. So there are no x-intercepts, and it couldn't be solved because there wasn't a variable left. Y-intercepts. For the y-intercepts, you let x equal 0 and solve for y. So we take our function and we put a 0 everywhere there was an x, and we evaluate that. It gives us 4 over negative 3, or negative 4/3. So the y-intercept is at the point 0, negative 4/3, and there were no x-intercepts. Next, we're going to put all of that information on the graph so that we have a starting place. We can kind of see the bounds that our graph is set within. So we know we have a vertical asymptote at x equals 3. A horizontal asymptote at y equals 0, so it's the x-axis here. And the only other point we can put on the graph is the y-intercept, which was at 0, negative 4/3, negative 1 1/3. Now here's our cross. We need to know, here's our asymptote at 3. We need to know what's going to happen to the left and what's going to happen to the right of that. And this is completely up to you which numbers you choose. You'll want to pick something close to 3, and you'll want to pick something maybe far away from 3. So I'm going to pick to the right of it, how about 3.5, and then a bigger number, let's say 7. To the left of it, 2.5 would be kind of close to it, not super close, but kind of close on the left. And I already have that point where x is 0, so I'm going to go ahead and use that. Okay, so let's see, 3.5. What I do is I plug it into my function for x, and I get 4 over 0.5, which gives me 8. So the point 3.58 is on our graph. If I put 7 into that function, I get 4 over 7 minus 3. Or 4 over 4, which gives me 1. If I put 2.5 into my function, I get 4 over negative 0.5, which gives me negative 8. So what this does is gives me a set of points so that I can get a little better idea of what the graph looks like. So I have the point 3.5, 8. So it looks like this one is above our horizontal asymptote. And I have the point 7, 1. So it looks like this one is going to follow the asymptote just like this. Okay? On the other side, 2.5, I'm down at negative 8. And then I have that point 0, negative 4/3. Like this one is going to follow this way. Now we had no x-intercepts, so we know these are never going to cross. We also have an asymptote there, which kind of restricts it. So here is a basic sketch of our graph. All right, here's another example, our second example of 4. Looks a little different. We're going to do the same thing. Find the domain. Again, you set the denominator equal to 0 and solve. And that gives you the number that's not in your domain. Everything else is except for 1/2. So my domain is from negative infinity to 1/2. And then from 1/2 to infinity. We need to find any holes. Once again, we don't have any common factors to cancel. You cannot cancel an x and an x because this x down here is attached to a -1. So there are no holes. Vertical asymptotes, again, you set the denominator equal to 0 and solve it, which we did up above. So our vertical was at 1/2. X equals 1/2. Horizontal, we look at the degree of our polynomial. Okay, on the top we have degree 1, and in the bottom we have degree 1 also. When the degree of the numerator and the degree of the denominator are the same, we divide the leading coefficients to find our horizontal asymptote. Okay, so it would be at y equals 3 over 2, or 1.5. And there would be no slant asymptotes, because that only happens when the degree of the numerator is 1 more than the degree of the denominator, and they're the same, not greater or less than. So let's find some x-intercepts. Okay, for rational functions, the x-intercepts, we'll set the numerator equal to 0 and solve that. And we get x equals 0. For y-intercepts, we let x equals 0, so we put a 0 everywhere there's an x, and we evaluate that. And we get 0. So our x and y-intercept are both the point 0, 0. We're going to put all of that information into a graph. So I have asymptote at x equals 1/2, and a horizontal one at 3/2, or 1.5. And I know I have a point at 0, 0. Let's put some more points in that are close to our asymptote 1/2. Anytime you have asymptotes, you want to plug things in that are close to it so you can see what happens on each side of that asymptote. So we're going to pick x values. To the right, let's say I'll do 1 and 4. And to the left, 0 would be easy, and we already know that one. And let's say -2, just to kind of see what happens on this graph. So if I put 1 into my function, I get 3 times 1 over 2 times 1 minus 1. Gives me 3 over 1, or 3. If I put 4 into that function, I get 3 times 4 over 2 times 4 minus 1, which gives me 12 over 7. If you're more comfortable with decimals, you can go ahead and divide that. It gives me about 1.7 if I round. And we got 0, 0. If we put negative 2 in, what do we get? 3 times negative 2 over 2 times negative 2 minus 1 gives me negative 6 over negative 4 minus 1, or negative 6 over negative 5, which is 1.2. So let's put those points on our graph. We have the point 1, 3, and the point 4, 1.7. So just above our asymptote there. So it looks like over here we're going to just follow those asymptotes like this. To the left, we have the point 0, 0, and the point negative 2, 1.2, so a little bit under our asymptote. And it looks like this is also going to just follow those asymptotes. So there is a basic sketch of our graph. All right, here is yet another problem. And I'm noticing that this one probably